provide any of this, you just use it. And I'm going to share with you the basic algorithm that's generally being used in there, and give you some history so that you understand where it came from. So I'm going to start with introductions with what's inside the MRC package, and then going through a few crucial steps in the image processing of one single image. If you go to the computing workshop already, we've basically gone through the process, the main part of the embedding already. So this will be the second time. So I'll go a little faster, but try to concentrate on the part that can go around so that you can see what happened. Okay. So the MRC packages has been around for 30 years, over 30 years, and it's developed ever since we had the BL structure. Should I use this? So it's been over 30 years, and it's developed by a number of people. The main part for the 2D crystal image processing are written by Richard Anderson, and a few of others by David Agar.
Why should be green on the battery pack? Should be, yeah.
I'll try to speak up. So the program mainly is written in Fortran, and the last time it has a major general update is in 2000, when they changed the image format so that it's compatible with crystallography packaging, CCP4. And at the same time, they changed the plots that's generated from the programs into the modern PostScript format. So what does it include? It's not just for 2D crystals. It still has, of course, some general processing functions, such as you need binning an image, so that's an area, doing Fourier transform, etc. And for the 2D crystals, okay? Okay. For the 2D crystal processing, it has parts for the image analysis, for the images acquired from the 2D crystals. So it also has processing programs for electron diffractions. Other than that, there are ones for helical reconstructions, things for single particles as well. And they keep on adding new things. So some of the new ones that, for example, here, it's I think it's added in 2005. Now the documentations. A lot of our earlier users have the problem that there's enough documentation on this package, making it harder to use. And there are a lot of the things that are around, and unfortunately you still have to read them. We can't go through all of them. And the most recent reference, if you need to reference the package, well, what I found is still the 1996 one, when they describe the whole package. And there are documentation with the package if you download them. And Henny did a great job in consolidating the available documentation in 2dx.org. So that would be a good places to find all sort of information. And one thing I need to mention is that this one that Vincent Unger and I wrote, mainly during about 1998, what we were doing is writing down our experience and what we know about each parameter, how to set them, and the sort of tricks in there. So if you do run into problems and then you need to make adjustment of your parameter, this would be a good place to start. And there are also help documents in 2DX application. I found that pretty useful too. I have when we wrote this, I also had something for electron diffraction in a similar manner as those. This currently is on my website, so maybe one day we'll move that over to CBS. Okay. The program header. If you are downloading new MRC package, a newer version of MRC package, and suddenly something doesn't run, those documentation may not help you because they probably are still pretty out of date. In that case, what you will have to do is actually go to the program source and look at the headers. This is where they would document the changes that made it into it. So in general, it will have the name, the purpose, who wrote the original version, and that's what's been changed in each version. And then there are so-called control cards. This will correspond to one line on your script. So for example, the first line will have 3 different inputs, and here explain what they do in a simple term. So using this information, then you can check against your script what you missed that's not in the new version. Okay. Now where do you get this? Other than the one that currently distributes with 2DX, if you want the full and updated versions from MRC, you have to contact Judy Short, and she will set you up for FTP download of the current version. Okay, so this is the introduction to the package itself. Any questions so far? Okay, so the next part I'm going to talk about is basically the processing flow. This is the packaging flow that's been used in for 2D crystallography. Has been pretty reliable. What they developed at MRC. So there are several parts to it. If we make it shorter, we can divide it into the parts. First, you eliminate the artifacts that come from your scanning or your CCD images. And you determine the lattice for your crystal. And what you need to do is try to boost up your signal to noise ratio for the repeating features of the image. In other words, the part that represents as a crystal. Once you've been able to optimize it as much as possible, then at the end, you will try to extract the phase and amplitude information right at the position of those diffraction spots. As Bob explained, since we have crystal, the information can be all condensed inside all those few pixels on your Fourier transform. So the way I'm going to describe this is always going a bit backward. The first thing I'm going to talk about is how the phases and amplitudes are extracted, so that then when you look at the other, you see why we are getting improvement. In the handout, the order is reversed, so you can find it a little bit at the end of it. So the program they use to extract amplitude and phases from the Fourier transform is called the MMBox, and the version now is called A. This program basically does a fitting of each of the spots according to your lattice parameters. It determines the amplitude and phases and something called IQ values. I will explain what it means and what it means. And then I will show you what's the result of the way they are doing this two parts. In the early days, and you can see that what they were doing is actually print out the intensity and the phases around it and create the contours and decide it by hand. So with the program, it becomes an easier job, from our perspective of view. What the program does is that for each of the diffraction spots in the Fourier space, it creates a box around it. So let's say it's, here is a 16 by 16 box. That's why it's called the MMBox. by having the spot with your diffraction spot in the middle, you can plot the amplitude and the phase in the spots separately. So what I'm going to look at here is that how they actually fix this. What they do is that they do a sync-weighted sum of all those values within this 2 by 2 pixels. There were reasons for doing so. In the early days, that when the program was developed, it's usually pretty large crystal. If you have the crystal as large as your image, then your diffraction spot will occupy only 2 pixels. And so they just started off like that. And the purpose of unbending is also trying to achieve to the point that everything is concentrated in that spot. So ideally, if you unbend everything, at the end, the whole image should be your crystal. So that's why it looks like this. And all those weighting has to do is to make it possible to fit things in sub-pixel resolution. So as a result, what you see is that here's the peak in amplitude that has a big variation. One thing to notice is that if you have a sharp peak, if you look at just the phase, within that range will have a very even phase values. And so that makes it the average a bit easier. At the same time, you need to estimate your noise level. So the noise level is estimated by doing a similar kind of fitting, but on the border of the boxes, where you assume there won't be any crystal information in there. Okay? Okay. Now, on the output, other than the amplitude and the phase, and then your indexes, there is such a term called the IQ value. IQ value was developed in a way so that it's easy to categorize the different phase error, that you different significance level of your data. So the way they decided to do was to determine it by the phase error. Well, actually, they determine the IQ value by the amplitude ratio between the amplitude through that sync function phi and the background. So as you can see here, we have the range from at the best IQ value will be 1, the worst one will be 8. In fact, there is a 9. 9 would mean that it's actually below your RMS background. It means that you don't actually see any signal. That's higher than your background noise. So as you can see this range, that we are actually not using, in many cases, we're not, say we go to IQ up to 5, you are below 2 signal to noise ratio. That's actually very weak peak, if you think about it. So it's not a very strong signal we're looking at in amplitude term. However, the phases that you can determine out of something with such a low signal to noise ratio is still rather significant. So the phase error that they figure out is between, go from the highest is only to 56, with 90 or 180 as random. So how this is figured out? Think about it this way. So this is the amplitude. We have amplitude, something that's very strong. Here's something that's weaker. Let's say that the natural distribution of your information is within a Gaussian hill, like this, surrounding the endpoint of this. If you look at the phase distribution, so the phase would be, phase is defined by whatever that angle is. So the range of the phase in this distribution of a high amplitude peak would have a very narrow distribution. However, if that's a shorter vector, a weaker refraction, then the range will be larger. So you can basically relate your amplitude values to a phase error that you will from now on use as your determining factor. Okay. So with those two things there, when we look at what the end result of this part is that we changed from a computed Fourier transform into values in the IQ into amplitude, phase, and also IQ values at each spot, as you can see on the right. So we often just look at the spot and see what's going on. Because of what I just said about how it's actually determining these values, there are certain things that you will observe. For example, here we are looking at the region around those two. You may find out that in your images there will be some strong but diffuse spots. Will come out with a very low IQ values. You look at the amplitude, it will turn out to be very low. This is because the fitting is only concentrated on those 2 by 2 pixel boxes. So whatever is outside of it is not contributing to your overall integration or your phase determination. And that also comes from a distortion. So what we will be doing in unbending is try to sharpen things like this up in order for you to be able to have that information considered as part of the crystal. Okay? Make sense now? Now the other consequences of that, remember I was showing that what the signal to noise ratios are for the different IQ cutoff. The signal to noise ratio is actually not a very large number. Our eyes can pick up about IQ 3. Anything that's higher than IQ 3, you probably won't see it. You cannot distinguish it from the background. You look at the Fourier transform on the image. Over time, there will be sparkle of noises everywhere. So there's, by chance, you're going to hit somewhere that it will have a peak that's bigger than 2 standard deviation, two signal to noise ratio. Then you will end up with the spots over there. So the way when you look at your final result is that it's important to realize that unless you get a group of the refractions that shows up with a good IQ values, otherwise if you see just sparking numbers at very high resolution, that doesn't mean that your crystal actually diffracted that far. Okay, because it may be just a random event.
Anchi, what happens if you have also the same one on the other side, if we did pair, can this be used as a judgment to say that one is actually a good spot rather than?
No, you cannot, because in the computed Fourier transform, this is generated directly, so they are always equal. So if I have a spot here, I have to have a spot here. This is really only generated, in a sense, on half of.
Just to follow up there, actually only the right half of the Fourier transform is even saved in memory, and the left half on the screen is just generated from the right half.
Okay, so one way of figuring out if this is real peaks is to actually make basically integrating all those boxes that I was talking about when I make the spot. Then you'll be able to see that maybe you add all those up, do you have a peak above the background or not? Okay. All right. So the next part I'm going to explain is unbending. So unbending is the most powerful tool for us to being able to increase the output to get the maximum of the amplitude and the phases. Get the maximum, get the best, a lot of spots into a good IQ value range. So what's unbending? Unbending really is no different from what they do with photograph. So you have a photograph that you take a picture from on the parking lot. And the building, because of the perspective distortion, it will not look like, it will look like the top part is shorter than the bottom. So people, they develop software to undistort this part, and then you end up with the image like that. So it's the same thing that we are doing here. There are several things that you need to do. You need to know the extent of distortion. You need to be, then you will be able to get it to okay. So here's the example, just and also the basic flowchart. The purpose of this is, say you have an image that, in this case, that you probably see it. You can see some diffuse spot in a certain area. That's not even showing up when you use the image box to extract the FT2 space. They don't show up because they are too diffuse. So the purpose of unbending is to make those ones become sharp enough so that when you extract it, you can get the information out. So here's the process. It consists of a few parts. The first is to define a reference that will give you a good contrast, with a good contrast. Because the raw image, even if you know where the reference is, there's no contrast. Computer will have a hard time to use that in the computation. The second thing that you need to do is to enhance the distortion in the same way so that you get a good contrast image in the same way as the reference. And then you will do a cross correlation between that. Then you use autocorrelation to create the profile of the reference in order to search on your cross correlation map. Once you quantify that distortion, then you can make the correction. Okay. So I'm doing is a little still. Here there are some images. Hopefully it will help you understand what I'm talking about. So for example, now we're just doing a Fourier transform. This is just part of it. Remember, Fourier transform it's to give you the same exact information as what you have in the real space. So it does not only contain where the crystalline informations are at the spot, and there are also the noise in the background. So what do we do to make it possible? Now I'm throwing it up so you can see the way we're doing the masking there. So to create the references, we mesh out only at where the diffraction spot is expected to. In other words, we are assuming that everything is perfect. When you do so, and then you back Fourier transform, you get a map looking like this. Okay. You should be able to see that you almost can see what this map is going to look like at the end. Okay? And you can see where the good patches are, where you have good contrast and it has a regular, a regular arrangement right around there. But the area that's basically just not crystal. So by looking at this, you will be able to create your reference. Now the other part when I was talking about, you need to keep the distortion information in order to make a correction. To do that, we basically create a mask that's a bit bigger. In other words, that anything, not only that frequency that's corresponding to a perfect lattice is going through, but also information that's around that frequency. It means that your, say your two molecules is separated apart right by your unit cell. Then this will, in the Fourier space, show up in the exact frequency of your lattice point. Now, if you are slightly off, then it will show up at a frequency that's slightly larger, right? Or the other way around. So because we know they are not off by a lot, so I don't have to cover the whole area. So we only have to make it to a little larger than where our lattice spots are. So this is what I was able to show in the computing computing practical. I hope you can see on here the distortion. You see that on the back? Okay. So because we allow the distortion information to go up, so you not only pick up what we had before in a very similar manner, and also you pick up the area that's especially bad. You can see how it started to distort around the different area. One thing I should mention is that this two process.
I think this is a remarkable picture, and actually what is sort of amazing to me just staring at it, where it looks really nice in terms of symmetry, you have in many places low contrast.
Mm-hmm.
Where you see very high contrast, there is something fishy. Well, it's difficult to judge because if you do not know how it should look like, you would perhaps go in for the wrong area for selecting your reference. You will come to that in the next, but I think one can see here so nicely.
Okay. So here is the trick to find out. So when you actually select the reference, you don't select it from the distortion map. You select it from the one that we only mess out only for the lattice information. So if you use that, you have a better chance of finding so-called the best area according to your lattice parameter. So if you are using this, you are more likely to go wrong. So, okay, so that's those two. Now we come back to the tightly masked part. With that tightly masked filtered image, then we can pass up what we consider as the best area on the crystal. It's usually a small portion of the image, and I need to apologize to those who did the practical on the first day. A question was asked, how big is the area that you mask? And off my head, that's between 10 and 20. And when I look back, it turns out that it's about 10 to 20% of the image what I normally use. And because of the way we normally scan it, that come out to be about 5 to 10 unit cells. Okay. All right. Now, so far, what we have been doing is using a reference right inside our image. There's another way of doing this. Once you get to the point that you already merge your data and create your very first 3D map, no matter how bad it is, you can use that as your reference. Then what you do is that with the 3D model, you can project it into the same direction of how you actually collected your image, this particular image. Apply the CDF to it. So as a result, you end up with something as a perfect crystal projected in that direction. This way, you can create your Fourier transform massing in the same way. It will always all come out because it's perfect. And then you can create your reference area from that. Okay. So you have different ways of creating reference area, but from either from your own image or from the overall 3D model. This program that's doing this is called the Matrix, and you would see that on certain Friday particle. Now we have the two different maps. One shows the distortion, one shows what the perfect crystal should look like. So you want to do is do a force correlation. And as Bob mentioned, correlation is a special, did you mention that about force correlation?
I said it's a kind of convolution.
Yes.
Yeah.
Yes, I remember hearing that.
Yeah.
So it's a kind of a convolution. So what you will get is that you have a sharp peak in the middle of it if you do autocorrelation of the same object. And you do cross correlation, and it will show up, in this case, that you will see a peak that's basically repeating in the same way as your lattice is. So you have one single peak per unit cells now. Now, what we need to do then is search on that to find out the distortion. So what they decided to do is that, okay, we're going to need to know the shape of those cross correlation peak in order to do a good search. So we are taking the reference area. When you do an autocorrelation on that, it looks something like this. Because we have it oversampled so that you can look at the subpixel shift in there. Then this is the middle of it, and it will repeat somewhat to the next unit cell, and then the next and next. But the peaks will become even weaker and weaker because the two-square convolution autocorrelation will end up with a peak in the middle and then the level down on the side. So in the process, we'll take just the middle part as our profile for our searching. So then we put that profile because the actual size is only the same as all the other peaks. And you just search along different directions. By doing so, you basically create your map, a list of the positions of each of the peaks, and also its height, compared with your autocorrelation profile. So this is the kind of output that you end up having. So this particular plot shows the height of the peak. So the darker overall appearance that you're seeing here means that it is a stronger peak. That means that it's closer to the perfect crystal.
I have a question. So in the previous image, there seemed to be double spots on the left side, and now you only have single correlation peaks. And this is somehow not obvious to me why this happens. So I would expect you would have double the number of correlation peaks on in this left area.
Okay.
How did it happen that you just get the single correlation peaks?
That has to do with the way they do the search. The way they do the search is that move by one unit cell in the search just around.
Okay.
In other words, you are ignoring the ones that you off by a lot.
Correct positions. So you miss the spots.
Right. So
actually, the other question then is, it's not a perfectly round profile, the autocorrelation profile. Now, if you've got a distorted crystal, which is, it's also a shift and a rotational shift within the crystal itself, does that cause problems?
for this kind of search, is only being able to handle shifts, not rotations. So if within a crystal there are rotations, this sort of distortion correction will do nothing.
So why not just use a circular autocorrelation profile? Why does the actual shape help?
The actual shape, sometimes you will have a peak that's pretty far from a circle. I'll show you something.
If you have a little rotation, by definition your correlation should go down. And if you don't do anything and then threshold, you throw those away. I think this is the basic trick one uses. You know, the refinement would be that you will run along and try to get the unbending taking care of the rotation.
Okay. Okay. So the other half of the information is how far it is away from where you expected it to be, as Deirdre was asking. And when it's a search, it doesn't just search continuously. It search at this point around it, find the peak, then shift to the next unit cell according to the lattice parameter. Search around there, not everywhere else.
If you would have a shift like half unit cell, which happens quite frequently, would you pick it up properly?
I don't think so. If it suddenly shifted by half a unit cell, it won't. But it's a gradual change over several unit cells, then it will be able to do.
Right. But this is one of the difficulties we often have. That, two lattices are perfect, but it happens that there is a crack and they are shifted by hand. Or if we do spot scanning, then there is no guarantee that one spot and the other spot are exactly in register, because between the two spot exposures you may have a small drift. So these are the little things that create headaches.
Yeah, I can see those in that.
Okay, just one question to your remark before. So you determine the position for your search, not from the central position, but relative to nearby positions in the search. Okay, yeah, and then you reveal the problem as half a lattice constant will not occur.
Well, yeah, if it does happen, then half of that won't be able to find. That's unfortunate.
Yeah, sort of a quick and easy solution to that we occasionally use is if you have a large crystal with one very obvious dislocation or several, you can polygonally mask out one region and do the individual processing as though they were separate images and then merge them together later. It's not perfect, but
Yeah, you have to do some handling.
Yes. For those kind of things, you just have to process them separately at different patches. Okay. So one thing I always want to point out is that this looks really scary because there are some of the distortion looks as if it's out by the holes in the cell, but this is 10 times of whatever it's actually distorted. It's not a very big differences. So the next part, once we have distortion value, we'll try to make the correction. The way it's being done is that divided the images up into grids, and according to your distortion and how far it needs to move, it shifts each part of it and fills up whatever is missing with the edge value of the other. So if you do this too much, you can see that you are actually going to create an artifact. This is one of the reasons when we do several rounds of unbending, you always unbend the original, not your previous rounds of unbending the image. All you are trying to do with extra rounds is to get a better estimate what the distortion is. Okay. So this is the main point that I want to do about whether you can check if something, if it doesn't come out as well as what you would like. The first is that the reference. If your reference area is supposed to look like this, and it ends up look like that, it's not good. For example, because we are looking for an area of your perfect pixel. If you just allow it to say, use all the spots as a certain IQ cutoff, you very likely that you'll end up with auto-correlation profile that looks like this. In other words, you have a definition, you can tell where this peak ends very easily in this direction, but not in the other. Okay. Whether that will cause problem explains doing the search, because in a direction it doesn't know its definition, it will not be able to search the peak properly. So it's a lot of time will cause a situation like this. So this one happens because I have a correlation profile looks like that. In certain direction, it's basically doing a random walk. It's pick whatever you can find. Because when we are making our references, it's not just one point. It's already several unit cells in there. The distortion we are getting, it's in a way, it's a smoothed out version. So whatever you are seeing, it should be smoothly transformed from one way or in one direction or the other. It shouldn't be zigzag like that. Okay? Okay, I think I'm almost. What's your time?
2 minutes.
2 minutes. Okay. So I'm going to just quickly touch on the boxing. Boxing, what we are talking about the boxing is basically masking of the real space in real space. We talk about the masking in the reciprocal space to boost the the signal to noise ratio. There is another way to do that, is do that in a real space. In other words, you only want to extract your amplitude interface at the lattice point of the area where you are sure to be correct. Okay. So this is what I would do with the image we still have there. So I would pick up, for example, 50% cross correlation, using a 50% cross correlation to create a polygon in here that use the box image program that will create from the original, something looks like this. Can't tell the differences, but once you Fourier transform that and create your list of amplitude interface, this is what you will get. What I noticed a lot of time when we do boxing is that the low resolution information has not changed. If you look at the non-local part, the non-local spots that's at the better IQ values, sometimes it's even when you box it, it's even worse than what you did not do it. Okay, this has to do with you're looking at a smaller area, so you have a fewer unit cells to contribute to that intensity. But if everything goes right, the part of your box contains higher resolution information. In other words, when you start to look at the ones at higher resolution, they should improve. Okay? So that's it. What? Now this is the last part. Basically, what I'm trying to say here is that the unbending protocol, everybody have a slightly different idea how to do it. But it has become pretty stable. That's why we can use the standard scripts in UDX to be able to do a reasonable unbending. If you look at a recent article, the description of what they do is very short. If you are looking for detail of how people have been doing their unbending, you need to look at an earlier paper. And oftentimes it will have a detailed description of how they deal with their particular images or images. So basically, the take-home message is this. MRC package has been around for a while, but the algorithm in there is pretty robust. So you can still, using the same principle, you can do quite a lot. Second thing is that your project, if everyone's project is different, so you may need to modify and refine it for your own project. I put this picture at the end because this is a wave generator. It's like a mechanical device to do Fourier synthesis. So they were using different wheels and to create a chart that simulated the wave. So it's a pretty interesting device. So that's it.